Okay, so welcome to Lecture 9. This is going to be more on op-amp non-ideality. Specifically, we'll be talking about input offset voltage and input bias current. But as usual, let's start with a few announcements. So first of all, you know Homework 3 is online and due Friday via Gradescope. Lab 2, I announced last time, is a 2-week lab. The pre-lab is not due this week, it's due in the second week, which will be next week for most of the labs. But for this lab, you should have proof of having started it when you go to lab this week. You will still do the lab this week, and you'll continue doing the lab next week. I mean the physical lab here, where we're actually measuring things and using the equipment. This Wednesday, I will be out of town. And so obviously this is why you are watching this video only by video lecture. There's no ground lecture on Wednesday. And I think those are all the announcements I need to make right now, so let's get on with the lecture. So again, the topics will be input offset voltage and input bias current. Last time we actually started input offset voltage, so I'm going to continue with that right now. And so on the right side, you can see where we left off last time. I defined what the input offset voltage was. I described pretty much what it is. And so it's basically trying to model the phenomenon where if you ground both inputs of your output, of your op-amp, you expect to have an output voltage of 0 volts in the ideal case, but in reality, you get an output voltage not equal to 0. Usually goes to the rails, and last time I expressed the rails as L plus or L minus. So L plus would be some large voltage like, I don't know, 18 volts, or L minus will be minus 18 volts in that. So anyway, the op-amp goes to one of the supply voltages, usually, if it rails out. And so the reason why it's doing this is because there are internal differences in the matching between transistors that make up the input circuit for this op-amp, which we'll talk about later on in this class. But for right now, a good model for this effect is to just put an input offset voltage, VOS. So typically the way that you would determine the value of this offset voltage is you take a real op-amp, you'd ground the input and output terminals, but you'd send a voltage, you'd send the terminal through a voltage source which you would set such that the output voltage is zeroed out, and that then is your offset voltage there. And typically the VOS takes values on the order from 1 millivolt to 5 millivolts. It could be also smaller too, for depending on what type of op-amp you have that you've designed. And so why do we want to model this effect? It's such a tiny voltage here, and it turns out that it's a tiny voltage, but it's at the input of the op-amp. And so any tiny voltage at the input of the op-amp can cause a very large change in the output. And so to see this effect, let's take a couple of examples. We'll take one example where it doesn't matter that much, but then we'll take another example where it actually impacts the circuit quite a bit to the point of making the circuit non-functional. Let's take the first example here. And for the first example, we will take a non-inverting amplifier. So a circuit that you know well, except now we're going to model this op-amp using the circuit above, meaning we will include the offset voltage in its model. So here's our op-amp. And I'm going to hook it up in a inverting amplifier configuration. So here's my inverting amplifier with a resistor coming in, a feedback resistor R2 going from the negative terminal to the output. And this time I'm going to model the input to the positive terminal as an input that has this offset voltage VOS in series with it. Let me make this clear here. And as usual with an inverting amplifier, I'm going to ground that. And I guess I'm going to take the case where I'm going to ground the input terminal of this op-amp. And so when I ground the input terminal of this op-amp, I expect the output to be equal to 0 volts. However, if you look at this, that's not what's going to happen. So this is meant to be an inverting amplifier. but instead of 0 volts, my output voltage is going to be equal to effectively this non-inverting amplifier configuration that I've got here. So if you look at this, the offset voltage is basically going into the positive terminal. I've got R2 and R1 in feedback, but this now looks just like a non-inverting amplifier if I take the positive terminal as the input. So this means that my output voltage now becomes VOS times 1 plus R2 over R1, okay, which means it's not 0. And so if I want to take a specific example here, if R2 over R1 was equal to 9, and I had an offset voltage of 5 millivolts, then in this case my output voltage would not be 0 volts. It would rather be 50 millivolts, since the gain of this circuit is 10. Okay, so that's one thing that's non-ideal right there, is that the output voltage is not 0, but how bad is this? Well, it's not so bad. Okay, so this is an effect of the offset voltage, but it's not a debilitating effect. Okay, so when do you run into something where this offset voltage can actually be debilitating? Well, let's take another example to describe that. And in this case, let's take another familiar circuit to you that should be familiar, and that's the integrator. And so the integrator circuit, you should know, looks like this. So I have my op amp, negative terminal, positive terminal, and going into the negative terminal I'm going to have a resistor R, and in order to integrate I'm going to put a capacitor in feedback here. So there's my capacitor C. And in this case, again, in my positive terminal, I'm going to model the non-ideality that is the offset voltage here. And as usual with an integrator, I'll ground the positive terminal. And I'll again take the case where I'm interested in what the output of this thing will be if I ground the input. And so if I ground the input, the output of this circuit, V0, should be equal to, not necessarily 0, but it should be equal to whatever the initial condition voltage is across this capacitor. And so say that's some voltage Vc across that capacitor. That's what we'd like it to be. However, that's not what it's going to be. And it's not what it's going to be because, again, I have this voltage at the positive terminal of this op amp. And so if I have this voltage at the positive terminal of this op amp, if this is negative feedback, which is what this is, then the voltage at the negative terminal, right, because it is an op amp, and we're saying ideal in all respects except for the offset voltage, that means the voltage at the negative terminal is also going to be equal to VOS. And if the voltage at the negative terminal is equal to VOS, that means I've got a voltage across this resistor R, which means a current is going to flow, which I'll call I1, going through this R. Now, since I'm assuming this op amp is ideal in all respects except for this offset voltage, that means no current can go into the negative terminal again, which means the only path for this current to take is through the capacitor. And if that current goes through the capacitor, that means it's going to charge that capacitor, and that means that the output voltage is going to be equal to the voltage at this node, which is VOS, plus whatever voltage is across that capacitor. And we know that whatever voltage is across that capacitor is the voltage that you get from the integrator function over a certain time of the time t, integrating that current over that time. And so I know what that current is, right? This I current is equal to VOS divided by this resistance R. And so I can then write this as VOS plus 1 over C, integral from 0 to t of VOS over R dt, which when I evaluate this is going to be VOS times 1 plus t over RC plus that initial voltage condition, which I'll call V sub C, at t equals 0. Okay, so that's now what my output voltage is equal to. And if you look at this, this is now a function of t. And so specifically, if I wanted to plot this as a function of time, what's this going to look like? So here's the voltage output is a function of time. This is just a straight line. Okay, it's going to start at a small voltage VOS plus VC right here, right? But then it's going to go up, and it's going to continue to rise until the op-amp saturates. So that's not a good thing here. Right, so this is VOS plus VC at t equals 0. Let me try this again so I can make that clearer. And this line just keeps going up until it hits the rail. Another word for that is to say until the op-amp saturates. Okay, so that's not a good thing. That means this circuit is unusable. You can use it for a very small amount of time, which is the time it takes for this output to go to one of the rails, but that's usually a very small amount of time. So we need to fix this problem. And to fix this, what we do is we basically force this op-amp to go to a specific voltage at the output. Right? And so one way we can do that is to put in parallel with this capacitor a resistor. So I want to put this in as a dotted line. So we're actually going to put this resistor in, call that RF. Okay, and so let's then call this our solution. And that's to place a resistor so place resistor RF in shunt with the capacitor. That means in parallel with the capacitor. And so that's the resistor RF that we're talking about there. And if we do that, then we end up with an output voltage V0 that's just equal to the original equation from this circuit on the right. Now you have a purely resistive equation at DC. And so your output then just goes to VOS plus whatever RF is divided by R in this case. Okay, and so that holds the voltage. It prevents it from going to the rail. Okay, this is a very effective circuit, but if you don't use that circuit, if you didn't know that you had an issue with offset voltage, then when you're actually hooking up a circuit in the lab, you would not be able to get an integrator to work. Okay, so it's actually a very important insight and understanding about op-amps to know that you have to put that large resistor. It's usually a very large resistor that you put across the capacitor because it's in parallel and you don't want it to affect the value of the capacitance. But it's very important because it takes the output and it locks it at a voltage much smaller than the rails. Okay, so that's input offset voltages, and that's a good example of when it can be very important in a practical circuit. Now the other thing that you have to worry about for many op-amps, and these will be op-amps that are based on bipolar inputs, not so much MOS inputs, although some of them you may have to worry about if they have biasing at their inputs there. But you need to worry about input bias currents. Okay, and so what are input bias currents? So many op-amps require small currents into their input terminals for proper operation. Okay, so these currents are independent of the input resistance Rn. Let me just write some of that down. Many op-amps require small currents into their input transistors that basically allow the transistors to function. Okay, and I should say the currents are independent of the input resistance Rn. That means the finite input resistance of the amplifier that we have modeled with the variable Rn. So let's go to the next page. That says over. Let me try to write that such that you can read that. Okay. And so schematically, what this looks like is as follows. So I would take my op-amp, and of course the symbol that I'll use for my op-amp is this triangular symbol, and I'll have an output to this, and I have an input going in. So again, I'm going to assume, just like before, that everything in this op-amp is ideal except for this input bias current. And so this will be the minus terminal, this will be the plus terminal, but the way that I modify it to model the input bias current is I put a current source on each of these. And so call this IB1, and here I'll call that IB2. Okay, so those are two input bias currents going into the terminals. That basically means that if you put anything here that goes to ground at this terminal here, this current is automatically going to, the op-amp is automatically going to draw current into it equal to the IB1. And you'll know why we're calling it IB, IB1 and IB2 later on. It's really the base current of a bipolar transistor if it's an op-amp using bipolar transistors. Now, this model here is equivalent to sort of a more general model that I can draw of this same situation, where instead of showing directly the currents as IB1 and IB2, I can draw the currents going into the plus and minus terminals as a combination of what's called the common mode and a differential offset current. And so the common mode current I can model like this, two current sources coming into, basically drawing current into both the negative and positive terminals, and both of these currents having the same common value I sub b, and thus the name common mode. But then to model the fact that the currents could actually be different, have two other current sources. Let me draw these a little further to the left. So two other current sources that model the differences between those. And see, this is called the offset current, IOS. So this one coming down from the top will be IOS. This one at the bottom will be minus IOS over 2. So this is sort of a difference value of current through that. And so if I'm equating these two here, that means that IB1 on the left side is basically equal to IB plus IOS divided by 2, and IB2 is equal to IB minus IOS divided by 2. And so the value of IB that you're saying here, this is kind of like an average or a common mode value. Okay, so let me write this down. So we have an average or what's called a common mode value. And again, we label that I sub B. And from just these equations up above, I can also write I sub B as equal to IB1 plus IB2 over 2, which is obviously the average value of that. And so this we will define as the input bias current. Okay, and so the typical value for this is on the order of 100 milliamperes. 100 nanoamperes for bipolar amplifiers, or I should say specifically bipolar op-amps. And so the other value that I'm interested in is IOS value. And like I said, the IOS value is the difference value. So I could say the difference or differential value. And that we give as a symbol IOS, and that's simply just equal to the difference between the two currents. So IB1 minus IB2. And so this is defined as the input offset current. And typical value for this current is much smaller, so on the order of 10 nanoamperes. For a bipolar op-amp. And so as before, we're going to be interested in the effect that this input bias current has on actual practical circuits here. And so, like we did before, let's just take some examples. So the first example, to keep things simple so you can see what's going on, we're again going to take our non-inverting amplifier. So here it is. Okay, so there's our non-inverting amplifier, and we're going to do the same thing as before. So the input's generally here, but what we're going to do is we're going to ground that input. And if we ground that input, we expect our output voltage V0 to be equal to 0. However, because this is now a non-ideal amplifier, where everything else is ideal except for the bias current, we're going to model our bias current. So this will be bias current IB2, and this will be bias current IB1 coming into there. And so again, this is a ideal in every sense of the op-amp except for these bias currents. So that means that this voltage at that node is going to be 0 volts, right? This is our virtual ground. And so if that's a virtual ground right there, then that says that there can be no current flowing through R1, right? So IB is not going to want to take any path through R1 there. So let me just write that there. So I'll just say, therefore, current cannot flow through resistor R1. However, current has to flow because I've got that IB1 right there. And so the only way that that IB1 can flow is through resistor R2. So I have that IB1 now flowing through resistor R2, which means that the output voltage of this thing has to be equal to IB1 times R2, okay, which I can write in terms of my specific common mode and difference or offset current using the equations above, which means it becomes this. Okay, and so of course this is not zero, and that is sort of an effect of this input bias current. So depending on how big R2 is, I could have a pretty good offset voltage V0 due to this current IB1 flowing into the negative terminal. Okay, so that may be an effect that I don't like. And so if that's an effect that I don't like, then I'm going to be looking for some kind of solution to this. So to reduce this effect, we're basically going to add a resistor to the positive input. So you can see right now at the positive input in this circuit to the right here, this current IB2 is just flowing straight through that ground there, and it's not creating any voltage across there. But if we can create a voltage here, then we might be able to take a current component here, which then absorbs the current IB1 and sort of cancels what voltage comes out to V0. So let's show this here. So we want to add a resistor. To the positive input. So here's the circuit we'll be looking at. So we have that classic non-inverting amplifier configuration still here. And that goes into voltage V0. But now, instead of just grounding this positive terminal, we're going to take it into another resistor, R3. Okay, and as before, this is a non-ideal op-amp, where the only non-ideality we're assuming it has are these input bias currents. So I'm going to draw them in. Okay, but now we have a slightly new circuit. And so we now have a situation where we are still flowing current through R2. So I'll call that current I2 there. But now I have a new voltage at the negative terminal. And that new voltage is going to be the voltage generated by IB2 going through R3. Right? And so that voltage is going to be minus IB2 times R3. That's the voltage that appears right there at the negative terminal. And so if I have a voltage at the negative terminal of that value, that means I'm going to have a current flowing through R1 here. That's going to be equal to that voltage divided by R1. And so that current here is going to take on the value minus IB2 times R3 divided by R1. And so now I have to account for both that current and IB1 in the current I2. And so if I write an expression for my current I2, that's now going to be equal to IB1 minus IB2 times R3 over R1, which means that my output voltage V0 is going to be equal to minus IB2 times R3 plus R2 times IB1 minus IB2 times R3 over R1. So this minus IB2 at R3 is just the voltage at the negative terminal, and then this voltage here is just the voltage that's generated by I2 across R2. Okay, so this is now our voltage, and obviously we've got things that can compete with one another. We've got negative signs and positive signs throughout this. And so we want to ask the question, what value of R3 makes this output voltage go to 0? Okay, so let's take the simple case where we have no offset current. So the only current going in is just the average current I sub B, or common mode current I sub B. Okay, so let's take that case. Okay, so in other words, IB1 in this case equals IB2 equals that average value IB. Okay, so in this case, I'm going to take this equation for V0 and just plug those values in. So this becomes IB, and then do a little bit of factoring here. This becomes IB times R2 minus R3 times 1 plus R2 over R1. Okay, and so if I'm looking for this, a set of resistors that will give me an output voltage V0 equal to 0, set that equal to 0, the IB disappears, and I can now write that R2 is equal to R3 times 1 plus R2 over R1. This means that R3 is going to be R2 over 1 plus R1, sorry, 1 plus R2 over R1. This then you can rearrange to 1 over R1, sorry, 1 over R1 plus 1 over R2. Therefore, if you choose R3 to be equal to the parallel combination of R1 and R2, you will get an output voltage equal to 0 for the case where the input offset current is equal to 0. So this is our solution here to set the output voltage equal to 0. So what does this say? This says that if you have a amplifier that has R1 and R2, say a non-inverting amplifier here that is using R1 and R2 to set its gain, and you want to make the output voltage equal to 0, even though you have input bias currents that are equal into both the negative and the positive terminals, then you want to take a resistor, put that on the positive terminal, and make its value equal to the parallel combination of R1 and R2. Okay, so that's very good insight there. It's a pretty simple case that we're looking at there, but extremely good insight into what we can do to solve a practical problem where input bias currents are causing a shift in our output voltage. Now, I specifically took the case where IOS is equal to 0, and so the other case that we can take is where the input offset voltage is not equal to 0. So in other words, now I have to write my IB1 as being equal to IB plus IOS over 2, and my IB2 is going to be equal to IB minus IOS over 2. Okay, and so it's the same game as that. I'm going to take that same voltage or same equation for V naught that I had before. So there it is on the left side there. Let me rewrite that. So that's going to be minus IB2 times R3 plus R2 times IB1 minus IB2 times R3 over R1. Okay, and so I'm going to go ahead and expand this equation here. I think I want to do this on the next page. I'll go ahead and do it on this side here. And so if I expand that, I'm going to get V out is equal to minus IB times R3. All I'm doing is I'm plugging in these values here, the IB1 and the IB2 from up here, and I'm going to write them in terms of the common mode IB and the differential IOS values. And so getting back to this is minus IB times R3 plus IOS times R3 over 2 plus R2 times the quantity IB plus IOS over 2 minus IB times R, I guess that'll be 3 divided by R1, and then plus IOS over 2 times R3 over R1. Let me be clear about the R3s here. Still doesn't look like a 3 necessarily, so there it is. Okay, so this is the equation that I end up here for V naught, and what I want to do now is plug in the solution that I had from above. So in this case, I'm not going to solve for an R3 that makes V naught equal to 0, but I just want to find out to what degree an input offset current will spoil that design approach, where we're trying to zero out the output voltage by setting R3 equal to R1 in parallel with R2. So if I do this, then this gives me, this V naught voltage then becomes equal to, let's see, IB times R2 minus R2 times R2 over R1 plus R2 minus R1 R2 over R1 plus R2, okay, and then plus the input offset current IOS times R1 R2 over R1 plus R2 plus R2 plus R2 R2 over R1 plus R2. Okay, and so we want to simplify these things here, and so this thing here turns into R1 R2 plus R2 R2 over R1 plus R2, and so we can see these are the same. So this term here is the same as this one on the right, those go away. This term is the same as the one in the first one, so all of these go away. And so this whole first term turns into 0. This term here you can rewrite as IOS over 2 times 2 times R2 times R1 plus R2 divided by R1 plus R2. So those R1 plus R2s cancel. This 2 cancels with the 2 from the IOS. And we end up then with this whole thing, V naught, just being equal to IOS times the resistor R2. Okay? And so we want to compare that to what we would have gotten here if we just had bias current times R2, which is what we would have had before, right? So without the correction using R3 equal to R1 parallel R2, we would have this voltage at the output. Okay? And so we want to compare the two of these. Well, IOS here is just 10 nanoamps, whereas this IB was 100 nanoamps. And then this IOS over 2 is about 5 nanoamps. Okay, but clearly this on the right is much bigger than what I have on the left, so it still helps. So setting R3 equal to R1 parallel R2 still helps, even if my input offset current is not equal to 0. Okay, so that's good news. That means that that design methodology that we're using to try to cancel the effect of the input bias current still is effective, even if you have some offset current. It's not perfect, but it's still very effective. Okay, so those are the last two non-idealities that we'll talk about for op-amps here. You'll learn about other non-idealities in other classes, and so other non-idealities include things like noise and really trying to model the nonlinearity in these elements. So we also will start modeling the nonlinearity in these elements, but we're going to model the nonlinearity in the elements that make up the op-amp. And so let's switch gears now to talking about op-amps to now starting to talk about what is inside these op-amps. Okay, and so in order to do that, and of course that means I'm going to talk about transistors, but before getting to transistors, let me first put in perspective what exactly a transistor is. And so to put that into perspective, I want to talk about circuit elements, but circuit elements that are generalized versus the circuit elements that you've probably seen in 16A and B. Okay, so let me title this Generalized Circuit Elements. Okay, so let's start with resistors. So you know the resistor circuit element. And what you know mainly is the linear resistor. Okay, so let's talk about this linear resistor. And so that linear resistor that you know takes on this circuit symbol. And if I put a voltage V across that resistor, a current I will flow through it, and I can write an expression to model that current as a function of that voltage as just being I is equal to the voltage divided by R. So it's a linear function. So if I want to draw the graph, or sort of graph that transfer function, and if the vertical scale is the current and the horizontal scale is the voltage, then this is going to plot out a straight line that has a slope that's equal to 1 over R. Okay, so that's our linear resistor. However, we can generalize this concept. So let's generalize the concept to a nonlinear resistor. Okay, and so nonlinear resistor, I guess in some of the early treatments of this sort of thing, gave the nonlinear resistor symbol look like this. So it's the same resistor symbol, except you put sort of a heavy, a solid bold-faced line where you have the negative terminal of this thing. Because now where the positive and negative terminal is matters for a nonlinear resistor. You'll still apply a voltage and you get a current, but now your current is a more general function of voltage. So for example, if I wanted to plot this, it may look something like this. So this is current versus voltage. Then instead of a straight line, maybe I have some curve that looks like that, right? It's a very nonlinear curve. And it turns out this is what most of our semiconductor devices do. Not exactly this curve here, but they're not linear like a linear resistor. They actually have some curvature. They're nonlinear, and that's what makes them more difficult to analyze if you don't know the correct techniques for analysis. And so a lot of this class ends up being learning the correct techniques for analysis of these nonlinear resistor type elements. So I should say, it's not only resistors that can be nonlinear. Your other elements that you're familiar with can also be nonlinear. So if we take the example of a capacitor, by the same token, we can have a linear capacitor which you know has this symbol, and I can put a voltage across that capacitor, and if I do that, I'm going to generate charge across the capacitor, plus Q and minus Q. And for a capacitor, usually you'll describe that as the charge you get after application of a certain voltage. So you'll plot charge versus voltage, and in this case for a linear capacitor, you're going to get a straight line with a slope, I should say slope, equal to the value of capacitance. Okay, by the same token, right, I can generalize this to a nonlinear capacitance. Okay, and so a nonlinear capacitor is going to take on that same capacitor symbol, like this, except again with a little box around it, and denote which is the negative terminal that will apply the voltage across. We're going to get a positive charge and a negative charge across it, but now if I plot the charge versus the voltage across this, this is now no longer a linear function. So on the left side for the linear capacitor, Q is equal to C times V, it's linear. On the right side, Q is just some function of V that is not necessarily linear. Okay? And so I should also say there are also nonlinear inductors. Okay, but we're not going to cover these because these are not found in low to mid frequency integrated circuits. I'll just say generally not found, or I'll say not seen. In low to mid frequency integrated circuits. So we're not going to say a lot about those. You might run into those again if you start taking a course like 142 here, or other courses in mainly communication types of circuits. So there you are. You have these generalized circuit elements, and so let's give an example of one of these generalized circuit elements. And a great example of this is something that we'll be seeing a lot of, at least parts of this device in this class, and that is a diode. A diode has several models. You can show several models for diodes. But all of which represent nonlinear resistors. So diode basically is a nonlinear resistor. Okay, so let's take a look at that. So even the ideal model for a diode. So let's take a look at the different diode models. So the first one I can look at is an ideal model, ideal diode. So you know that an ideal diode, if I were to plot its transfer function, so again plotting current versus voltage, and giving this this device the ideal diode symbol, which usually is your diode symbol, which you may or may not know right there, but it's this triangle with the bar across it. But put a circle around it to mean it's an ideal diode. So there's the voltage, there's the current going across this ideal diode. But the transfer function for this ideal diode then looks like this. Okay, so it's either zero current flowing for any voltage below a certain threshold. Well, if it's ideal, the threshold will be 0 volts. And then as soon as you get to 0 volts, you pass that threshold, suddenly your current goes to infinity. And that is an ideal diode right there. And so, of course, there are no such things as ideal diodes. And so if you want to get closer to reality, you can define what's called a constant voltage diode. So in this case, the IV curve is also 0 current all the way up to now a threshold voltage, which I'll call VD0 for the on voltage of the diode. So that's my diode on voltage. And this is usually from 0.5 to 0.7 volts. Okay? And so once I get to that on voltage, that's where I suddenly get that infinite amount of current for this. And so this is closer to what a diode does here. And in order to model this diode, oftentimes what you'll do is you'll take the ideal diode, which has a turn-on voltage of 0 volts, and put it in series with a voltage source, a DC voltage source, that has that voltage VD0. So the voltage that we were applying across this is this little v, and that then is the current that would go through this. Okay, so that now is a little more accurate to what an actual diode does. Okay, looks like I've run out of pages. Let me add one more page here to finish this up. Let me put several pages in. And so finally, these are all, the first one is an ideal model. The second one is getting closer to reality, which is a constant voltage model, but still is not exactly what happens in a real diode. And finally, what you get is an actual diode. Okay, so in this case, the IV curve for an actual diode looks like this. Okay, so I'll go all the way out here and plot current versus voltage. But an ideal diode does have very near 0 current for all intents and purposes. Let me get this a little straighter here if I can. Yeah, I don't know if that's much straighter, but anyway. Right, so it has nearly 0 current for a long range of voltages below a certain threshold voltage. So your threshold voltage is going to be right here. So you have still a diode on voltage there. And so I'm saying it's a near 0 current, but let me be a little more accurate about the way that I'm drawing this. So I apologize, I keep drawing this there. But the current is actually a little bit below 0. Right, so it's actually some negative current going up there. And then once I get here, it starts going a little more positive, and then it pushes up, and it comes up very quickly. But it doesn't come up immediately with that. So I get a curve that sort of looks like that coming up for the diode. And this is the diode current below VD0. And then there's another voltage right here where I suddenly get current in the other direction for this diode. So an actual diode does this. And the symbol for our actual diode is just going to be the diode symbol. Right, so I'll put a voltage across that diode symbol. This is an actual diode now, and if we talk about an actual diode, now we have the current equal to not suddenly going to infinity at VD0, but basically taking on the form IS, where you have some saturation currents, what's usually called there. So IS is defined or given the name saturation current. But it's going to be this I sub s times an exponential function of that voltage. So it's usually V over some N times V sub T. V sub T is a thermal voltage. So that's at room temperature around 25 millivolts. And that's really Boltzmann's constant times temperature divided by the unit charge. And I've already called it what people generally call it, which is the thermal voltage. Okay, and then this minus 1, where the minus 1 models the negative current going for voltages below your threshold voltage. And so N in this case is either 1 or 2, and it's 1 generally for integrated circuit diodes. It's 2 for discrete diodes. Okay, so this is what an actual diode does here. This is its transfer function here, and this is something now that we want to spend more time, more focus on here. But before doing that, and we're going to do more of that in the next lecture, but the last thing that I want to say is that a diode I've been describing as a nonlinear resistor. But I do want to say that a diode is not only a nonlinear resistor, but it also includes nonlinear capacitance. And we're going to see that this nonlinear capacitance is going to be very important in the operation of not only a diode, but especially of a transistor, which contains a diode. Right? And so, if we want a more exact model for a diode, then it would look like this. So I'll take my real diode symbol, where I put a voltage across this, and I'll get a current according to this transfer function that I have on the right side. But this I can really equate to a circuit that consists of not only a nonlinear resistor that models that transfer function. So this is a nonlinear resistor where the diode current here, so I'll call this current going through this, I sub D, is going to be equal to some function of the voltage, which is, I'll repeat, that I sub S times E to that voltage times NVT minus 1. Okay, so it'll consist of that current there, but it'll also consist of a component of charge and possibly current if it's an AC input, which it generally is, that's governed by a nonlinear capacitor. So I'm going to have a plus Q and a minus Q across this, and there's the other terminal of the diode, Okay, that would be the total current going through the diode, and the total voltage would be applied across this whole thing. And it turns out that this charge for the diode, as we'll see, is going to take on some other function of voltage. I guess I'll give it an F double prime of voltage. That's going to be equal to the unit charge. Well, let's not call that little q, because that's the unit charge. Let's call it a big Q here. So this charge here will then take out the unit charge times the doping concentration NA/ND, where Na is an acceptor doping concentration, Nd is a donor doping concentration, times the cross-sectional area of the actual diode, times the width, times the square root of 1 plus a voltage divided by a potential. Okay, so the voltage is the reverse bias voltage. Right, so V sub R is going to be minus V in this case. And I'm giving you more information than you need right now. We're actually going to find out where this equation comes from later on. But this now becomes the equation for the charge across a nonlinear capacitor that's inside the diode that sort of adds to the current that's going through the diode, that's dictated by this exponential equation, and that takes on this curve on the right side. Okay? And so what we're going to do in the next few lectures now is explain why a diode behaves this way by actually looking at the inside semiconductor part of that, and that will then allow us in the future to start talking about transistors, which basically contain diodes among other things. Okay, but I think with that we'll end this lecture now.